Now we recording. Let me turn this focus. So now we went off here last time. We were talking about projectile motion, right? Now the main hold on. So that kind of brings us back of what we were doing before, right? The main thing that we were talking about, we did all this math, right? We did all this math, all this stuff about vectors, vector scalars, going back into that, bringing that back in here. Then we talked about the different type of vectors we knew. And then we started getting into all this math, understanding magnitude and direction. Then we did vector addition. And then we talked about key components about having a vector component, right? So talk about the east and west components, north, south, which really relate to X, Y, in two dimensions. Then we talked about trigonometry. How do we use trigonometry to be able to find these components, right? We're still talking about math. And then when we use trigonometry, we get these components, we have the actual arrows and how they add together, right? So now then we use more math, Pythagorean theorem, to find out the missing side of a triangle, right? But we represent these vectors in a triangle format. So where now we can use Pythagorean theorem to find like the resultant vector or the different components, right? So that's what we did right here. And then we ran through a couple of these problems so that I could show you the specific triangles that you'll see all the time, like a 45-90 triangle, or a 30-60-90 triangle, or 3-4-5, or 5-12-13. So like these are the different relationships that we see within these triangles that we can also see and help us out with vectors. And we see now with this, right? We were able to play around what we knew about the special triangles to find out the different components of the vector to find the overall result, which is our last vector. Still doing math, right? But then we started getting into the relative velocity and river flow problems, right? So this helps us understand like what does that mean when we have these different components that we added them, right? So like the headwind, tailwind example, like if you're flying a plane, we're going in the same direction, we're adding wind in the same direction of wind, so we're going to go a little bit faster. If we're going opposite direction, then we're going to go a little bit slower. But now if we're going at that plane going one way and then the wind going to the side of it, now we have those vector components to where we have to do either vector addition and then we have to add a final resultant. So that's what we get. At the end, we actually have to create that triangle and put it together and find out what that is. And so that's actually using what we did all together, right? And then we just spam that to get it into the riverboat problems to where now we're talking about how does that work when we have one river or one quantity going in one direction and we're trying to go across to where now we create this different triangle. So now with us creating those triangles with that vector addition, how can we take advantage of that to get to our desired locations, right? So now we're getting a little bit more into physics. So now we look at the boat headings and then the speeds and how that plays a factor into us getting to one of the positions A, B, C, or D. And we ran through these so where we were able to go ahead and see where we would land off at, right? And I think that also has got us to now, when we put it all together, the conceptual part in the math, to where now we can actually predict and determine speeds, we have to determine times and distances to where we're going and going downstream within that same riverboat problem. And that's where we left off last class, where I did do some calculations. I messed up a little bit at the end, right? But the just was we have that same riverboat like over here, and then we're going across. So now we need to figure out how fast we're going across, plus the way the river is flowing, and then what that resultant is. Like that's the first part, finding us the resultant. And then once we have the resultant, we go by the individual components because now we want to figure out the time it takes to cross the river. Then we want to figure out the distance the boat will travel. So that's when we start using those definitional equations, or maybe using some kinematic stuff that we use from unit one to be able to apply that to now what we learned about vectors. And that's what today's class is going to be. Really bringing it all home. We learned about vectors. We learned about the basic kinematics in the first unit. So now how do we put all that together to where we now start to analyze the situation, which we call projectile motion? Some of you guys have already started, like, think lab 4, and I believe lab 4 start talking about projectiles. So when I throw something up in the air, or if it travels across, it has usually a parabola type shape. And we us having that parabola type shape, we're able to actually predict where it can land at, how far to go, how high it can go. just like the Michael Jordan problem, right? But now we're really getting in depth with understanding the traveling part of it, right? So in this problem that we have today, right, I'll just tell you straight up, this one's going to be more of a half parabola, what we've been seeing to before, right? And I didn't focus too much on the full parabola motion because of the fact that the question that I pulled for us to like bring it all home is a half parabola. So I wanted to make it 1-to-1. But when you do the practice problems, and like I said, when you do the practice problems, actually take your time and do them, you'll see full parabola. So full parabola is not just a free fall motion or something being shot out. Full parabola is actually I literally throw something up in the air or I launch it, it goes all the way up, and then it comes down. Like that's full parabola. And you have a few problems like that. So I want you to try those out too, so you can see the difference of when we have an actual initial velocity and we're not just starting from just a free fall or just an initial launch. But this one right here, what was I about to say? What you call it? Sorry about that. Now with this one, right? We have yes, twofold, right? So the way that this problem works, right? Just so I can explain it, we're looking at projectile, right? So we're gonna have two situations, right? We got a baseball and we have a cannonball, right? So now what we're looking at is we want to examine the difference between what we've talked about before in the first unit, which is free fall, and then now this projectile motion where we actually shoot it out, right? So now let's think about it, right? I have this marker that's in my hand, right? I have this marker in my hand, right? What does it look like if I have it and I just drop it? What type of motion is that? That's free fall, right? Now, if I take it and I throw it to Peter, right? Projectile, because I did what? Projected it. Yes, he throws it back to me and I catch it, right? He actually put some horizontal speed on it. He put something on it to where now it's actually moving horizontally while it's also doing what? Moving. It's moving, right? But how is it moving? Is it going to just stay level vertically? It's vertical, so it's dropping. So you see it dropped a little bit, right? Like I throw it back to you, right? That was terrible. But like you see how it's going parabola, like as it's going perfect. It's going horizontal. It's still falling at the same time versus if I just drop it. Did you see any horizontal change in speed? No. So that's what we want to see. Let's look if we can see if we can estimate this type of difference with the free fall example. Sorry, with the two example with the baseball and the cannonball right here. So let's set it up. We have the baseball, right? And what are they doing with it? They're literally holding it, and then they just do what?
Drop it.
Drop it, right? Cool. So now we drop it, right? So let's imagine that one. Let's what was I about to say? Let's analyze that one all together, right? I'm moving over to the board. Give me 1 second. Can you see the board?
We can see it.
Is that better? All right. So I gave a little hint, right? Over to the side. Remember when we were talking about free fall? We talked about the different type of equations that we can use, such as like the definition equations or the kinematic equation, right? So when we're using free fall, right? There was 3 different kinematic equations. Do you remember which kinematic equation we used over and over and over with the free fall? You don't have to remember the name, but you can look at the slides. Because I gave a hint. Displacement. That displacement one, right? So when we had our kinematic equations, right? I think it might be small kinetic, right? We had this one, I think, right? No. Yeah. Oh, yes.
I
That
can't
one.
really see that.
I want to take this down and put your camera to the screen.
Is that better?
Hold on, I'm trying to zoom in. What does it say?
Is this better?
Oh, yes.
Okay. Then I think we had it was displacement, something like this, plus over 2 times delta t. Yep, it was that one. And it was this one. This is the one right here. Right? And we also have this one, right? Yeah. These are our 4 kinematic equations, right? But when we did free fall, right? Like I gave the hint, we focused a lot on this one, right? So then when we go into the specifics of free fall, right? What was specific about free fall that we identified? Free fall. I have my marker and I go and I drop it, right? That's free fall, right? If I start off with this equation, right? Let me analyze as best as I can each individual component, right? Let me start off with this one. With my initial velocity, right? If I'm in free fall, my initial velocity, I'm in free fall. I'm just like the baseball, right? I'm holding it. And then I drop it. But when I start my motion, what is my initial velocity? 0, right? So now I can say my initial velocity is 0. This is in free fall. What does that do to my equation? Let's see. You just said this is 0, right? So let me put in 0 right here.
Just becomes happy.
Exactly. So now my initial velocity is 0. So now with this being 0, all of this now becomes 0. So I can rewrite this now as 1/2, acceleration times time squared, right? Okay. Now let's analyze it one more time. This is free fall, right? I got my marker and I dropped it. What causes my marker to drop? Gravity. Gravity, the force, or the what due to gravity? The acceleration due to gravity. Because the acceleration due to gravity is how much? 9.8 meters per second squared, which is the acceleration. So now, can we say that our acceleration is going to be equal to the acceleration due to gravity? So that would mean our acceleration is equal to. Exactly. So now substituting this 9.8 for A. Let's do that. So now I can come here. Now I can substitute in 9.8. So now if I simplify this, what's half of 9.8? So in the case of free fall, how far I travel, like my displacement from my initial to my start, is going to change by 4.9 times the time squared, regardless of its mass, regardless of what's going on, because I'm just looking at gravity and how it accelerates literally each time, and my initial thing is 0. So now we have this new improved equation right here, right? But this is what we see when we had that last free fall problem in section 1. This is what we see. Same thing with Michael Jordan thing. Seen this type of relationship before, right? So now we're understanding this, right? Let's start here with this baseball problem. So, what is having a baseball problem, right? I'm actually not going to look at it right there. So, what we want to do is take this baseball problem and be able to model it over here. And then you kind of see in like the top right corner, there's a little table right there. So we want to actually model this to where we make this table, right? So what does it have? It has the time and the displacement, really the Y, for the baseball. And so for the different times, we have 0, 1, 2, 3, 4, 5 seconds. Yep. We want to find out the Y. So this is in seconds, and the Y would be the meters. This is where we like the displacement, right? So we want to figure this out for the baseball, right? So let's do the first one together, right? Let's just do simple math. Let's plug in T right here in this equation. So we got 4.9 times 0 here. What is 0 squared? 0. So D displacement is equal to 0. Now, that was math. Now let's logically think about it, right? At time 0, where is the baseball at? It's still in my hand. So did it travel anywhere from its starting position yet? No. So logically, it makes sense that 0 means it's at its still its starting position. So now I'll do the same calculation at T equals 1. So now we do our displacement here, and now we do 1 second squared. What is 1 squared? 1. So 4.9 times 1 is 4.9. So that's the math behind it, right? Now, logically, what are we saying? After 1 second, the baseball has dropped how far? 4.9 meters. Because acceleration, 9.8 meters per second squared. So now 1 second has traveled 4.9 meters from its initial spot. That's the displacement. So now, let's do the same calculation for 2, right? So let's think about it. After 2 seconds, here's the math behind it, right? Our displacement, we got 4.9 times 2 squared. What's 2 squared? 4. What's 4.9 times 4? 19.6. So now we know our displacement is 19.6. What does that mean in physics? After how many seconds? 2 seconds, our displacement is now 19.6 meters. So from where we started at my hand, we should see the baseball around 20 meters after 2 seconds. Does that make sense? Because we're still in free fall motion. Real quick, I just did the first 3. Let's finish out the next 3. Somebody help me out. Give me 3 seconds. What would I do? Why'd you do 4.9 times 9? 3 squared is 9. So then you get 4.9 times 9, which is 44.1. Good. Then, how do we do 4? (4.9 times 4 squared). What is 4 squared? 16. So then we have 4.9 times 16, which is 78.4. Last one, we got 5 seconds. How will we find out for 5 seconds? 4.9 times 5 squared. What is 5 squared? 25. So we got 4.9 times 25, which is how much? Now, this is just like us doing a review. And this is free fall. This will be covered in the first part, right? But this will lead us into understanding projectile motion because now we're just going up and down here and just letting gravity, the acceleration due to gravity, dictate how this is moving, the baseball, right? And what we see is it's pretty predictable. Same like half parabola shape because you see the t squared. We're literally just going to just keep going down and then displacement is going to increase between from where we started to where we finish at. Simple enough, right? Now, what they do want to is, I believe, is to mark this on the little diagram over to the side, right? Now, real quick, just because I don't have it accurate, it's just like a little cliff, right? So if I start here, right, holding the baseball, and let's say, what is it? 20 each. We just want to mark the different spots on here as we go. So I'll do it in blue, right? So initially we start at 0. This is us at 0, right? Then after 1 second, we're a little bit like up here. Then after 2 seconds, we're almost at 20, about 20 pretty much. 3 seconds, we're about a little bit or 40. 4 seconds, we're at almost at 80. 5 seconds, we're past 120, right? Probably not the best, but what could you see about the motion of the baseball from just me doing the dots? What do you notice? How do you know it's accelerating? Now, Courtney, you said it online. You said it's constant. What makes you say it's constant?
Because the pattern is in the same direction.
So it is in the same direction, right? But what Victory just said, actually, Victory, come off mute and say what you just said again while I mute myself.
I said that it's accelerating because the dots are getting wider as it goes down.
Oh, okay.
Did you hear what she just said?
Yes, I didn't know how to say that.
No, good. So like, and it's also it's a little tough because I got the glare and I'm on the board, right? But she noticed right away too that the space in between the dots is increasing. So now with that increasing, that means that we have a distance increasing over time between them, right? Which means that the rate at which the distance is changing, which means that the velocity is changing over time, which means that the velocity is changing over time, that we have acceleration. But we can notice that by just saying, oh, this baseball, the distance is getting farther and farther and farther as we go down. That's where we see acceleration. Now this, once again, is all review. Now we got to go back to the example of when I was with Peter, right? And I'm throwing it to him. Because now we've added what component? Horizontal. First we were just doing vertical, now we're doing horizontal. So let's look at the cannonball example, right? The cannonball example, we're shooting out the cannonball horizontally from a cannon with the initial horizontal speed. I just added the word initial, but it says horizontal speed of 20 meters per second. So now we have something going in the X and in the Y. So let's look at that. And I'll start off with just doing a basic graph for the a basic table for the cannonball, right? Let's do the same thing, right? Let's see how this changes over time. Now let's think about it. This should be pretty easy, right? Let's start with the one we just did, the Y. Remember what I said earlier when we broke down this equation of free fall? Did we have to
Can you
consider
move the board over? I'm sorry. I mean, yeah, or the computer, the board. The board is probably easier.
this better?
Yes. Yes, thank you.
Okay. When we did this and we broke down the equation for free fall, we looked at the what? What is this? The initial velocity. And then we considered that because we're starting from here, we have a 0, right? But then we had to look at, and this is just in the Y direction, just going up and down, right? Then we looked at the what? The acceleration, which is acceleration due to gravity, right? Which is always constant, 9.8, it will never change. So now we have that, so we were able to put that in here. So now we're able to represent our displacement as what? This equation, right? So now, did we have to take into account the mass of the object? Did we take into account the surface area of the object? So does any of that matter? So if I was to be dropped from a cliff, would I have the same results as the baseball? How? How does that work? But I weigh more than the baseball, and I'm bigger, surface area wise. Crazy, right? But does it matter? No, it doesn't matter, especially if we don't have like air resistance and stuff like that. We're doing it. But like what I'm saying is we're going to expect to see the same results whether we have a different object, right? So let's take that into account when we have the cannonball, right? With our Y, right? How can we describe the motion of the cannonball vertically with this same equation, right? Am I changing anything? So essentially, what should I get when my Y, when my T is 0? 0. Right? Because if I just do 4.9 and I do 1, I get 4.9 squared. So 1 squared times 4.9, which is 4.9. Same thing if I do at 2, right? 2 squared is 4. 4 times 4.9 is?
When you're done, can you move the board over a little bit? I just can't see all the way to the other side. Where you're writing at right there, I can't see that. Yes, I can see it now. Thank you.
19.6, right? So now we can see that these are going to be the same, as Lakshmi just said, the same as these over here. So what do I get for 3? 44.1. What do I get for 4? What do I get for 5? Now that's good, right? Cool. So we see the same in the Y here as we see with the baseball. But the real question is where do we see the difference in the motion? Because in free fall, we dropped it. But now when I have a projectile that's coming out, it's moving also, not just vertically, but what's the other way? Horizontally. So now let's think about this horizontally, right? This is, I'll write it up here. So now, let me do it like right here. This little space. projectile, right? Let's use this same equation, right? Up here. Because we want to find displacement, right? Horizontally. This is what we did when we found it in the Y, right? Now we need to find it in the X. So let's do the same thing, but just in the X. So now let's do the same thing and analyzing each part of it, right? For this one, right, in the X, is our initial velocity still 0? In the X, as in horizontally, is it still 0? Let's look specifically for this problem. What did they tell us in the beginning with the cannonball?
Since launch, it has a speed.
I mean, when it's sitting in the thing, yes, but let's evaluate the motion as soon as it's launched, because that would be the different when it actually moves, right? So when it's launched with what?
For speed of 20 meters.
But is that 0? No, so it has some type of initial velocity. So for this actual example, we have initial velocity. So we can't just put it at 0. So for this one, it's actually what? You said it, just read it. 20. So for this specific example, we know the initial velocity is 20. So let me rewrite my equation now in for the X, results in what we just seen. Now I have here (20) times delta t, right? Okay, so now I have it plus 20, right? Now let's think about this horizontally, right? Horizontally. When we're vertical, do we have acceleration? Yes, you have what? Gravity, acceleration due to gravity, right? But that's in what direction? The up and down, so the vertical direction. Now, horizontally, do we have acceleration present? No. Gravity works vertically, so horizontally, we're not going to have an acceleration unless we have some type of force that's acting upon it, like a friction or initial push or a pull. Does that make sense? So now with us understanding that, right, what does that result to our equation? For our acceleration technically is equal to 0 in the X. So now how does that result here? Now I can rewrite this for my X for projectiles to say this part is constant. For this example, we have 20 times t plus 1/2 times 0 times delta t squared. What happens with all of this? This becomes 0. So now my new equation for my X is 20 times delta t. Now, we're over here, we have acceleration present, and we see that it's changing, right? What does it show us about the distance here? Displacement. What type of relationship is this? Oh, this would be better if I did it that way. Yes, because remember we had this. What type of graph is that? Parabola, right? What type of graph is this? It's not a curve, but there we go. type of graph is that? Linear. This one relates to this situation by us having a square, right? This one relates to this situation. And they're both talking about what concept? Position versus time, right? So now if I take the slope of this one, I should get some line like this, which is now my velocity time. If I take the slope of this one, I should get a line that's what? Horizontal, which is my velocity. And then lastly, if I take the slope of this, I should get something horizontal. And if I take the slope of this one, I should get 0. And what does that mean in physics? Blah, 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 blah. The acceleration, is acceleration present? Yes, we have a constant acceleration. Constant acceleration, which is gravity. That's this situation over here. In this situation, acceleration present? No. That means we have constant velocity. Yes. Now, let's think about that in projectile motion. I'm throwing something across. It'll continue to go horizontally this entire time, right? But where will it change its distance? The rate at which distance changes over time. When will it change? In what direction? The vertical. Just like a 5 Peter, one more time. Horizontally, it traveled, it was constant, right? But where did we see the change at? In the vertical, because over time, as he threw it back to me, it started falling closer and closer to the ground, but it still traveled horizontally at a constant velocity. Now let's see that with our math. So if we know this is our constant equation, right? Let's do it at each time. So now we go here at 0 seconds. What's 20 times 0? 0. So it's still the same thing. Like I didn't shoot it out yet. So it's still 0 right here, right? But now after 1 second, how far do I go horizontally? 20 meters, because how did you get 20 meters? 20 times 1, so you go 20 meters. After 2 seconds, how far do I go? Horizontally. 40 meters. How did you get 40 meters? 20 times 2. All right. Do the last 3 real quick. How far would I go after 3 seconds? 60 meters. How did you get 60 meters? 20 times 3 seconds. 20 meters per second times 3 seconds. How would you get after 4 meters? How far would you go horizontally? 80 meters. How did you get 80 meters? 20 times 4, 20 meters per second times 4. The last one, how far would you go horizontally after 5 seconds? 100 meters. How did you get 100 meters? 20 times 5, 20 meters per second times 5. So then we fill out this table and we have this for the cannonball. So not only are we traveling vertically, we're traveling horizontally. But you see the difference. One relationship is linear, it's constant velocity, while the other one has a variable velocity, which means it has constant acceleration. Different acceleration over here. Acceleration because our velocity is changing. And what does that look like in a graph-like motion, right? This one, this is nasty. This over here was just going straight down, right? Let's look at how they want us to graph it over here. I want to come down here. What do I have? 1, 2, 3, 4, 5, 6. Wait, oh. 1, 2, 3, 4, 5. Because that's a 0. And then 1, 2, 3, 4, 5, 6, 7. All right. right? This is exactly what you see right here. So now we want to take these, right, and actually plot these together almost like a coordinate system. How they go together, right? So for the first point, we start at what is our x when t equals 0? What is our x when t, what's our y when t equals 0? 0. So I'm basically up here, right? 0, 0. Now let's go at 1 second. At 1 second, what is my x? 20, right? So I'm over here. Now what is my y? 4.9. So I'm about like right up here. All right. Now for my 2 seconds, what is my x? 40. So I'm over here. And then how much is my y? Actually 0.6. So I'm about at 20. Right? I'll do right above 20, right? Now going over one more time. Where would I put my 3 seconds? 60. And then 44.4. So I'm about right here. What about at 4 seconds? I'm going over to 80, and then what? 78.9, so about 80 again. So that one matches up almost perfectly. Okay? All right, what about my last one? 5 seconds. You go over to 100, and then where do I go? 122.5, right? All right. Just in case you don't see, I'm going to trace it. That's me just tracing the points. What shape does that look like? Half parabola. A half parabola. Now we just seen the math make sense for how we see something travel. But if I throw this marker across the room, in which direction will it travel? Just visually when you see the marker moving. In a what type of shape? Parabola. And we see the math match up in the same direction. So this is projectile motion in green right here versus free fall right here. Free fall just goes straight down. Yes, we do see it change over time, but when we add the horizontal component, that's where we get the parabola shape. So projectile motion, expect to see parabola shapes. So we did all of that right now. When we put it all together, right? Now let's answer a couple questions. Out of these two balls, right, the cannonball and the baseball, which one do you think will hit the ground first?
The baseball.
Hold on. Look. First, look at the math, and after you look at the math, think logically.
Oh, the cannonball.
Look at the math and think logically.
That's what I'm saying.
Just look. Take 2 seconds and look at the table we just did.
The cannonball.
Look. Say it louder, Victory. Actually, come off of mute.
They'll both be the same.
Think about it. The ground is determined off of what? Horizontal or vertical? When we think about the ground, right, are we looking at vertical or horizontal? The ground. Technically, okay, yes. But like, if I'm thinking about, for the baseball, right? The ground is based, it's jumped up at a height, right? It has free fall. For me to figure out when it hits the ground, I'm going to look at what component, the Y or the X. Y. Same thing for the cannonball, right? So let's look at the Y. For me to figure out which one, and let's say let's just throw an arbitrary number, right? Let's say the cliff is 125 meters above the ground. Or 100, let's make it very simple. 123 meters above the ground. So for it to hit the ground first, right? And when, that means that the times need to be different in one of them, right? So now, when we're looking at the travel in between the baseball and the cannonball, are any of the times or distance different?
The cannonball goes farther, but
Yes, horizontally. But think about it. When we're saying about what? When it hits the ground. So it might go a little bit farther, but when will it hit the ground? At the same time. Now that's logically, but also look at the numbers. If it's 120 meters, 23 meters above, I just said 123 meters. But if the cliff is 120 meters high, right? When does it reach that point about for the baseball? 5 seconds it traveled 123 meters. It means it will hit the ground after 5 seconds. Now let's look at the cannonball. We need to figure out when it travels 123 meters, that's when it's going to hit the ground. When does it hit the ground? Based off of this. 5 seconds. Are those times different?
No.
So typically, without air resistance, they do what? They hit the ground at the same time. Does that make sense? Yes. Okay. And that goes back to our earlier point of talking about when we do kinematic equations and with free fall, right? When we're talking about the y, the weight doesn't matter, the size doesn't matter. We still get that. That only comes into play when we start talking about air resistance. Okay. So when we compare the two diagrams, this is very important, right? We want to compare the two diagrams, and can we talk about the effect that an object's horizontal motion has upon an object's vertical motion? Let's talk about the effect that an object's horizontal motion has upon an object's vertical motion. Before you say anything, look at the numbers. What effect does an object's horizontal component have against the object's vertical component? If you think I'm trying to trip you up, not me, or if the question is trying to confuse you or give you the trick up, yes, it is. So look at the numbers before you answer.
if both the like calculations completely separate from each other.
Mhm.
So they don't have any relation.
So you're saying they have no relation at all? Sorry, do they have an effect upon each other? As in, does my horizontal motion affect my vertical motion or vice versa?
These lines.
Say it again.
Oh, no, I was talking about these lines. I was looking at the lines.
Does my horizontal motion affect my vertical motion?
No.
Thank you. The answer is no. We can see it with the math, right? This one's changing with constant velocity. But does that affect how this one is changing with acceleration? No. So me just throwing a little horizontal does nothing to change the fact that it's going to have the same values as this one over here. So my horizontal has no effect on my vertical motion. Now, does my vertical motion affect my horizontal? No, vice versa, it's the same. Now, what does that mean about projectiles? What that means is with projectiles, right? The X and the Y, the horizontal, the vertical, they are perpendicular of each other. Perpendicular to each other, and perpendicular components do not have an effect on each other. Perpendicular components do not have an effect on each other. So they're separate entities. So we just put all that together, check our answers. Does this make sense? Does this look good? There's a lot going on this board. So if you're in person, I would suggest you take a picture of it before I erase it. Not gonna lie to you, there's a lot. It gets to the boring parts of physics to where it's like, I know sometimes you probably want to tap out, but trust me, we're actually making good progress. The fundamentals are what you need to really understand stuff if you really want to actually dive more into this. Obviously, most of you are just taking this class because you just got to pass this to move on for your graduation requirements. Yes, I understand that. But if you truly do want to just understand just a little bit about how motion works, a little bit about the world, understanding just a little bit about physics, please pay attention to this stuff. Because it does seem, for some people, it might be easy. So you just be like, I'm going to check out. For some people, this might be a little bit complex where you're like, I don't know if I want to pay attention. I'm going to check out. I'm saying fight with this. Because if you can understand this, the stuff like quantum, the stuff like engineering, the stuff like any other science, honestly, even chemistry and biology, like it makes so much more sense if you understand this. And I know that's kind of confusing to think that me dropping a baseball or me shooting a cannon will relate to molecules or relate to life sciences and cells, right? But it actually is all related. It's all related. So if you can get this, you can get a lot of things in science, which means that you be able to understand how a lot of things work. So we're making good time to be able to finish. I might not be able to introduce 4 today, which is all right. We'll see how this problem goes, but at least we'll finish 3 today. So we'll see how it goes. But if I don't get to 4 today, then I'll definitely start off next class with that. And we should be good. We got about 20 minutes left, less than 20 minutes. All right. Now we have reached the point where we're trying to get to our end goal, right? So this is the third question that really summarizes all of this, right? So a soccer ball is kicked horizontally at 15.8 meters per second off of a top of a field house and lands 33.9 meters from the base of the field house. Determine the height of the field house, right? I done gave the whole answer. That was crazy. Let me just stay right there first. All right. First thing we want to do, let's just draw what we're talking about. Here, right? I got my soccer ball.
This is the same like the one we just did.
So I'm doing my job well. Good. There we go. Because when you kick this soccer ball, right, how is it going to travel? Anybody play soccer? Football? You play soccer? You used to, right? So if I kick this ball, right, off a cliff, how do you think it's going to travel? Like what type of shape?
About half parabola.
Half parabola, right? So you expect it to be something like this, right? Now what we expecting it to be something like this, because it'll kick it, might go a little up right here, but like we're about to be here. Now, I kicked it and it lands somewhere over here. We actually have a little information, right? How far does it land from the top of the field house? Sorry, from the base of the field house. So say this is the top of the field house, the base is here. How far does it land from the base? So between here and here is 33.9 meters. It comes out when we kick it initially with a velocity of how much? In what direction? horizontally. So I can literally make my vector of the soccer ball going this way, right? Horizontally. All right. And we want to find what? The height. So we want to find out what this is, right? How high is the field house? Now let's think about it, right? Projectile motion. We can actually model this, right? In the same way we just did. Lakshmi, you just said it, right?
Yeah, the same form, the displacement formula.
Mm-hmm. So let's do it, right? Because we're dealing with what? Is this free fall or is this more projectile? Projectile, because we have a horizontal and a vertical. So let me write it as projectile, right? So now when we have projectile and we know we have a horizontal and a vertical, that means we need to have the displacement, but in two horizontal and vertical. So let me do one for horizontal. I'm going to use the first schematic equation. Twice. Well, this is technically the third, but you know what I mean. So we're starting there. So we have to do two separate calculations, right? The horizontal and vertical. Now, let me go back to where we started at before, right? In this problem, right, we still have our given, assume, assumptions, and unknown. What is the unknown? The height. So we don't know the height. Or in terms of here, the displacement in the y, right? This one right here, we don't know this, right? But we are given what?
Displacement in the X.
The displacement in the x, good. Which is how much? Careful. 33.9. There's displacement in the x over here. That 15 though is what? What is that 15.8? Hold on. It's kicked off with a what? Velocity. In what direction? Horizontal. Now is that what velocity? My initial final change of velocity? It's my initial velocity. Good. So I'm gonna write this two like this, right? And then this one like this. And even let's do this one like this and this one like this. So now my initial velocity in the x is 15.8 meters per second. Okay, that is my given. We have our unknown. Now let's talk about this assume. What do we assume in projectile motion? What can we assume? Based off of the problem we just did, what did we assume? What's always present? Say louder. Gravity is always present. So therefore, we have a what due to gravity? Acceleration due to gravity. And that's in what direction? Up to down. So that would be my vertical or my y. So now I can assume that my acceleration in my y is equal to what did you just say? My acceleration in my y is equal to gravity, which is how much? 9.8. Good. All right. Now, is gravity present in my horizontal? Horizontal. Which way does gravity go? Up and down. Does gravity go left to right? So do we have any other form of acceleration going left to right? Are we all consensus no? So therefore, I can assume that my acceleration in my horizontal, left and right, x is equal to 0. Other assumption? All right, last one. Same concept, right? Initially, what is my velocity when it first starts traveling down? Horizontally, we know our initial velocity is what we kick it with, right? But technically, that's in what direction? Oh, remember what I just said. Horizontal and vertical components are P word, right angle, intersect, pen, perpendicular, which means they're independent of each other. So one doesn't have an effect on the other. And what does that mean? That means that even though my horizontal velocity is 15.8 meters per second, it has no effect on my vertical initial velocity. And what we just seen from the free fall motion, when we have something dropping out the sky, its initial velocity is 0. So my vertical initial velocity is, so we can assume that x or
Oh, final? No,
you said x. What is our initial velocity in the x?
oh, and the Y?
Yes, we're looking for the y. Because we just found the x because the x is also which we said we have a horizontal because the kick is at 15.8. So now we want to find it in the y, but we just seen from free fall that the horizontal initial velocity is equal to 0. So we have everything we need now to really analyze this, right? I didn't want to write it like that, but it got to be like that. All right. I'm going to start now with this, and now this will take like literally the last 5 minutes, and then we'll be out of here. All right. So now what I'm going to take is hold on one second. All right. We're going to take this one right here and start here. So now I'll just start plugging these numbers. We want to find this, right? Actually, no. Actually, no. Let's do it like this. We want to find this. This is our unknown. We know the initial velocity in the y is equal to 0. So let me put the 0 right here times delta t, right? Then we got 1/2. And then we know our acceleration, acceleration in the y is equal to 9.8, which is gravity. I delta t, right? I get to do my calculation, right? This part becomes 0. And I have 1/2 times 9.8 times t squared. Oh, remember we got here? What's half of 9.8? 4.9. Does this look familiar? Does this look familiar? We just did this, right? All right, we can find our displacement, right? Can we? All right, what is it?
We don't have.
Oh, we don't have t. So how could we find t? And t is really what? The time what? It hits the ground. We have to find out the time it hits the ground. Now let's think about projectile motion, right? We can figure out how far it travels, right? Like how far it goes. And that time is going to be equal to the time, however far it goes horizontally, will it hit a certain point in the vertical at the same time, or does that happen separately? The same time, right? So if I find the time in the X, can I use that for the Y? So we can actually just come over here and do what? Find T, right? Now, what will we need to find though? Did they give us anything that we could work with? Horizontally. Let's see. We have a what? Say it louder.
Displacement and velocity.
You have a displacement. Oh, so they told us, we don't know what time it lands, but they told us how far it goes when it what? Lands. So now I can put that in here to start me off, right? So now I have 33.9 because when I start with this, right, they gave me this one equals, what's my initial velocity in the X? 15.8 times delta T, right? Plus 1/2 times my acceleration, which is what? 0 in the X times delta T. Now all of this becomes 0. So now I'm left with 33.9 meters equals 15.8 delta T, right? Now can I find out what delta T is, or the time that it happens when it lands? How would I do that? Because we have a what? We see multiplication by how much? There we go. So now I'm going to divide 15.8. 15.8. So what's 33.9 divided by 15.8? It should be about like 2 something, right? 2.1. 2.1 seconds. That's the time it takes for it to hit the ground. Now, can I take this time and plug it in over here? So let's do that. Because it happens, if it hits the ground over here at this time and it's this far away, it's going to be the same time over here. And now I'm going to put that 2.1 over here. So now I should get, what is 2.1 squared? 4.41. Then multiply that by 4.9 and you get what? 10 what? 21.609 meters. I'm not big on sig figs, so you could just say 21.6 meters or 22 meters, whatever, right? That ends up being our height, about 22 meters. Did you say 21.6 or 22.6? .154. Hold on real quick. .1 times 2.1 times 4.9. But if you do 2.145 times 2.145, 4.6 times 4.9. Okay. So just include if you want to be exact, it's 2.415, 2.415. Then you get about 4.6. Actually, yeah, be this exact because this is the answer that's going to be on the final exam. And then you get about 22.6. So this is the answer that I use on the final exam right here. 22.6. 22.6. That's the answer. But you see it right there and you see how you figure it out. But this is the process of how you go about it. First, to wrap up, right? Draw a picture. Draw a picture first. Sketch it out. And think logically what's going on. Then once you have your picture, start filling in the given, assume, and unknowns based off of your diagram. They gave us this. Sketch it out. We're trying to find this, which is the height. So now you sketch that out. And you also can see how it's being kicked off. And you have the vertical, horizontal velocity. Then once you get there, recognize what it was. If this was free fall, we would just be using this one over here. If it was just free fall. But since it's projectile, we have some X horizontal and some Y, so 2 dimensions. Then once you get there, now you have to find the individual components in each direction, right? In the X and the Y. But know that because it's projectile, things happen at the same time. I'm traveling horizontal and vertical at the same time. So certain qualities like time can cross both parts. So time. But my acceleration in my X is different than my acceleration in my Y. My initial velocity in my X is different than my initial velocity in my Y. And my displacement in my X is different than my displacement in my Y. But that time, because it happened at the same time, you can go back and forth with it. So we're done with 3. And we will be starting 4 on Wednesday. So we'll see the same thing with 4 on Wednesday, where we start looking at the same type of vector and X and Y components, but just with forces. This one should move pretty fast, and I hope I can bring it all together to where it makes sense, but we're actually on good pace. Let me stop the recording real quick.